Gonna start recording. There it goes. Okay. Switch back over. Okay. So on here on number 1, it says, what is the order of increasing, meaning more exothermic, enthalpy of hydration? So first off, we have to know what enthalpy of hydration is, which when you watch the video, I did get through that section. So that's kind of the second part of 15.1, where it talks about enthalpies of solution and hydration. And so essentially we're talking about the energy that's involved with like dissolving a solid ionic compound in water. And so basically, because that involves breaking apart the solid ionic compound, and then it also involves surrounding those ions with the water molecules, there's 2 parts to making a solution. The first part is the lattice enthalpy, because that has to do with breaking your solid ionic compound apart and making those gaseous ions. And then the second part is the enthalpy of hydration, which is I'm taking those gaseous ions, like right here, and I'm surrounding them with the water molecules to turn them into that aqueous solution, okay? And both of those together, when you add them together, that gives you the enthalpy of the whole solution, the whole process. And so when we talked about enthalpies of solution hydration, there are some factors that affect them that you'll see in your notes. And so this one says, what's the order of increasing? And so if you look through your notes, there's a few things that affect them, or a couple things. The size of the hydration enthalpy in your notes, it says it's determined by the attraction between the ions and the water molecules, okay? And the attraction is affected by 2 things: the size of your ion, so your ionic radius. So this is going back to topic 2 with our periodic trends. The smaller your ion, the stronger the attraction, and therefore the higher the enthalpy of hydration. Okay, so that's kind of how they're connected. So smaller ionic radius means stronger attraction, which means higher hydration, higher enthalpy of hydration. The other thing that affects it is the charge. The greater the charge, the stronger the attraction, and the higher the enthalpy of hydration. So since they're asking us the order of increasing, that means that over here on the right side, these are going to be the high ones. Over here is going to be the low ones. Okay. So I can already tell based on charge, 2 of these are backwards. Because I just told you that the greater the charge, the stronger the attraction, so the higher the hydration enthalpy. So which 2 can I eliminate based only on the charges?
B and C?
Nope, other way.
Oh, A and D.
A and D, because the higher charge is going to be stronger attraction, so the higher charges are going to have the higher hydration enthalpies. Okay, so A and D are out because the charges are in the wrong direction. So then between B and C, we got to figure out, okay, which of these are in the correct order for ionic radius? Okay, so this is where you have to think about your periodic table. Okay, sodium and potassium, which one is going to be smaller based on where they're at on the periodic table? You can get one out or look one up if you need to.
Sodium?
So yeah, because sodium, excuse me, sodium's in group 3. So the sodium ion, it loses that valence electron. It's only got 2 energy levels. The potassium ion, it starts out in period 4 and it loses its valence electron. So it's only got 3 energy levels. So sodium ion has 2 energy levels. Potassium has 3. That means sodium is smaller. Same thing with calcium and magnesium. Magnesium is in the same period as sodium. So when it loses these 2, it also has 2 energy levels. Calcium is in the 4th period with potassium. So when it loses its 2 valence electrons, it goes down to having 3. So either way you look at it, potassium and calcium are going to be bigger. Potassium and calcium ions, they're going to have the bigger radius because they have more energy levels. Sodium and magnesium are going to be smaller because they have less energy levels. So between B and C, which has these in the correct order for the increasing enthalpy of hydration? What do y'all think? So between sodium and potassium, which one did we say is smaller?
Sodium.
Sodium is smaller, and between calcium and magnesium, which is smaller?
Magnesium.
Magnesium. So this is the one. C is the one that has them in the correct order because it has the positive 2 charges over here. They're going to be higher. And then when we look at the atomic radius, potassium is bigger than sodium. So sodium will be higher than potassium because it's smaller. And then calcium will be higher because of the charge. And then magnesium will be higher than calcium because of its radius being smaller. So this is using those 2 things that are in the notes, talking about that the ionic, the size, the ionic radius, and the ionic charge are what affects your hydration enthalpy. All right, so number 2, which equation represents the standard enthalpy of atomization of the bromine molecule? So remember, atomization, that's where we're taking our diatomic molecule, we're breaking that bond. So we're cutting it in half and making the 2 bromine ion or 2 bromine atoms. They're not ions yet. That's a different step. So which one do you guys think is the correct one?
B.
Why B?
Because it broke the bond and it made 2 bromide atoms.
But so did C.
Oh.
So what makes one more right than the other?
The state, like if it's a liquid or a gas.
Yep, it has to do with the state. If you remember all of those statements last time, all those terms of like, enthalpy of atomization, ionization energy, all those when we talked about, they all talked about everything being in the gaseous state. So naturally in its standard state, standard form, bromine's a liquid when it's a molecule. But when you go through this atomization process, you break the bond and it turns it into a gaseous atom, okay? And so that's why B is got to be correct over A. Wait a minute. You know what? I think there's a typo. Because, okay, the key says it's A, and I think it's because this is supposed to be a half. I was looking at this and I was like, is that 12? I think that, okay, so A is supposed to be correct because it's supposed to be half. Like it's supposed to be 1/2. Because for the standard enthalpy of atomization, it's only to make 1 mole of the atoms. So A is correct because but it doesn't look right because the half, it looks like a 12 or it looks like a 1 and a 2. So you're still correct, Princess, on that it does have to be the gas one, but because of the way this is written, it's a little tricky. Like it makes you think that it would be B because that looks like a 12, but that's actually supposed to be a 1/2. And the reason it's that is because then that gives us 1 mole here on the product side instead of 2. We want to have 1 mole. Typically everything on these enthalpies, it's always like to produce 1 mole of something. Okay. All right. Which equation represents lattice enthalpy? So we got to remember what is the definition of lattice enthalpy and then what would that look like in an equation form? So we just kind of talked about it on that last part about how it has to do with their states. So remember the lattice enthalpy is where I break down 1 mole of my solid ionic compound in its natural state into the gaseous ions that make it.
Is it B?
It's B. So this one is just knowing that definition. It's knowing that lattice enthalpy has to do with taking a 1 mole of a solid ionic compound and breaking it apart into its individual ions. The only catch is the ions are now gaseous. So it has to be B. It can't be like D or C. Okay. And it can't be A because sodium chloride, the ionic compound has to start as a solid. Jennifer, Curtis, are y'all here with us today? Y'all are very quiet.
I'm writing stuff down, miss.
Okay. Yeah. I'm just making sure. Okay. So this one, which statements? Don't y'all love these questions where you have to figure out which statements are true and which ones are not? These are like the best questions. All right, so which statements are correct for ionic compounds? So we have to read all three and check to see which ones are true. But remember on these, sometimes if I can eliminate one of them, if I know one of them's not true, then I can get rid of sometimes multiple answers. You know, like for example, 1 is in both A, B, and D. So like if number 1's not true, I know it's got to be C. Number 2 is in A, C, and D. So if number 2 is not true, then I know it's B. You know, number 3 is in B, C, and D. So if number 3 is not true, I know it's got to be A. So even though there's multiple things to kind of read and consider here, you know, keep in mind if you can eliminate any of them, sometimes you can narrow the answers down really easily. All right, so number 1, lattice energy increases as ionic radii increase. So this is from, you know, directly from your notes. There were also factors. There were factors that affect the enthalpy of hydration. That's what we talked about, like on question 1 or 2, whichever one we did earlier. But there are also factors that affect the lattice enthalpy. Okay. And so when you read the factors that affect lattice enthalpy, it's the same thing. It's the charge and the ionic radius. Okay. And on this one, it's kind of the same thing. The charge is the same thing. So the charge, the charge on an ion, the higher the charge, the stronger the force of attraction. So the higher the lattice enthalpy. For the radius, as it increases, so as your radius gets larger, that decreases the attraction, which means lower. So small radius are going to have higher. So similar to the hydration one. So it says, so lattice energy increases as ionic radii increase. That is not true. Okay, it's the other way. The smaller ionic radii are going to have the higher lattice energy, just like the smaller radii had the higher enthalpy of hydration. So just reading number 1, now it's not true. Guess what? I just eliminated 3 of the answer choices. That means it has to be which one?
C.
Yeah, it has to be C. And I mean, if we double check, you know, just to verify, number 2, it says within the same group, the melting point of salts tend to decrease as the radius of the cation increases. That's true because remember, as your radius gets bigger, you have more metallic bonding going on. So that typically is going to lower the melting point. It's going to melt more easily. I'm sorry, the melting point of the salts. It's the ionic compound. It's not the melting point of the metal. I'm sorry. So it's not metallic bonding. But your melting point is going to usually decrease as you get larger because those forces of attraction aren't as strong. And then number 3, it has to do with solubility. So solubility in water depends on the relative magnitude of the lattice energy compared to the hydration energy. That is true because, as I said in your notes, that's the definition. So the solubility, that's that enthalpy of solution. And that it's calculated by adding your lattice enthalpy and your hydration energy or your hydration enthalpy. So both of those go into, you know, whether something's going to dissolve or how much it's going to dissolve and all that kind of stuff. So C is correct on that one because 2 and 3 are true, but 1 is false. But again, you're saving time. If you know 1's not true and you look at your answer choices, you can know it's C. Okay. Which equation represents enthalpy of hydration? So this is where enthalpy of hydration is we're making, so enthalpy of solution is where we're making a solution. So we're taking a solid ionic compound and dissolving it into the aqueous ions. So the 2 parts of that are the lattice enthalpy, which is where it looks like this one, where we take the solid compound, we break it up into the gaseous ions. And then once we have the gaseous ions, in order to hydrate them, they have to be surrounded by water molecules. And so enthalpy of hydration, the only one that's going from a gas so it kind of looks weird because we don't have the chlorine or the chloride, but the only one we're starting with in the enthalpy of hydration has to do with the fact that you have a gaseous ion and it's being turned into the aqueous ion because it's being surrounded by the water molecules and hydrated. And so the only one that goes from a gaseous ion to an aqueous ion, so only that state changes, is B. So C is actually the lattice enthalpy, because that's going from the solid compound to those gaseous ions. D is the enthalpy of solution. So if they ask you for the enthalpy of solution, that's D. That's the whole process. So that's gone from, you know, the solid to the gas ions, and then the gas ions to the aqueous ions. That's both parts together. But the only one that shows us, even though it only shows us the sodium, it doesn't show us the chlorine. The only one that's hydration is B. A is not right because A is this doesn't start as an ion. It has to already be an ion before it gets hydrated. All right, number 6, the Born-Haber cycle for potassium oxide is shown below. What expression represents the lattice enthalpy in kilojoules per mole? So this is what we were looking at last time, where I told you you'll start off with, so here from here, where it has 2K that's solid and half of an oxygen that's gaseous, when it goes down and it produces the product, that's the enthalpy of formation. Okay, because we're forming 1 mole of this ionic compound from the standard elements, the elements in their standard state. So this is solid, this is gas, okay? So that's the enthalpy of formation. The lattice enthalpy is this solid ionic compound breaking down into the gaseous ions, okay? So when you construct this cycle, usually you have your elements in the standard state. You do the atomization, where you see now this one's a gas, right? And this one is only 1 atom, right? We got rid of the half and the subscript. So that's going to be my atomization enthalpy. Then I get the ionization energy. And in this case, there's 2 potassium, so there's 2 electrons that it added, okay? And then from there, then to go up here, I'm doing my, this is my electron affinity for oxygen, because oxygen went from, you know, the atom to it's going to take these 2 electrons and become that oxide ion. So literally we're breaking down the process of how are these elements forming the ions and then forming this ionic compound. And so there's all these little individual steps that happen. And so in your notes, it tells you how we can kind of add these up, because I'm trying to get this total, the lattice enthalpy. Okay. And so I have my energy of formation is negative. So I start here, right? So I have a positive 428. I would then add another positive 838. Then I would add a positive 612. I'm still going up. They're all positive. But then for this one, see how it's negative, but it's pointing this direction, right? So since it's pointing this direction, it's negative, it's going the opposite of the way the lattice enthalpy is pointing. And so I subtract this negative number because it's pointing the opposite direction of all the other ones. So I'm going to go, as I go up, I'm adding. And then when I go this way, I'm subtracting, but I'm subtracting a negative number. So the setup, it would look like letter B here. And the reason is because, again, all these are positive because they're all endothermic. This one is enthalpies of formation or exothermic. So since I'm going for the lattice enthalpy, I have to subtract because it's a negative, and really I want to add it, because remember in math, when I subtract a negative, it becomes positive. So if I add all those together, that's going to tell me the lattice enthalpy. So that's going to tell me how much energy would or enthalpy energy it would take to break up this compound into these individual ions in the gaseous state. So again, you didn't have to do the math, but you had to understand kind of how this cycle, how this visual works in order to figure out how to set it up to get to letter B. All right, number 7 is really similar to number 5. Which expression, which transition represents an enthalpy of hydration? So let's see if you can figure out which one it is. I'll let y'all look at it for a minute or two.
Miss, are there only 2 pages? Because I only see A and B.
Oh, can you see it now?
I can see it now.
Okay, I guess I had to scroll or something. That's weird. So think about what we did up on number 5.
It wouldn't be A and B because it does not have the charge.
Yeah, exactly. So remember, it's already got to be an ion. And what state does it have to be in?
Gas. So
Gas. So
D.
it's D. Because it already has to be an ion in the gas state. For hydration, all we're doing was taking that gaseous ion and we're hydrating it with the water to make it aqueous. So that's D. Yeah, the A and B are like totally. B is showing the whole. So B would be the equation if they asked you for the enthalpy of solution. That's showing the whole overall process. I start with this solid ionic compound. I end with 2 aqueous ions. And so in between, we have this hydration and lattice enthalpy where we break these apart into the gaseous ions and then we hydrate them and make them the aqueous ions. So if you, those of you guys that haven't watched the video from the other day yet, when you get to that, it goes through pretty much everything. I had to